Here we're asked to evaluate by making an appropriate change of variables the integral, the double integral over r, a region in the xy plane, of x plus y e to the x squared minus y squared dA. And our region in the xy plane is the rectangle enclosed by x minus y equals 0, x minus y equals 2, x plus y equals 0, and x plus y equals 3. And if you were to graph these lines, you would see that the region R makes for a poor integration choice in the xy plane because of the limits of integration. We have basically a diagonally oriented rectangle. So what we want to do is change the variables, and it makes sense to me, given the expressions that we have, if we let u equal x minus y and let v equal x plus y. If we do that, then we can see that u would have limits of 0 and 2, and v would have limits of 0 and 3. And as we saw before, the choice of which one is u and which one is v is arbitrary. It wouldn't matter which one, if x minus y was u or x minus y was v, as long as one of them is one letter and the other is the other letter. Now, just by making that choice of u and v, we have come a long way with the integral. That is to say, we can replace x plus y and x squared minus y squared in the integrand with expressions involving u and v. We have our limits for u and v. What we don't have is the Jacobian, and in order to get the Jacobian, we need to solve the equations that give us the inverse transformation for x and y. So let's look at that. I'm going to rewrite here just so it's in front of us. U is equal to x minus y, and v is equal to x plus y. And first what I want to do is eliminate y to get x as a function of u and v. If we take the first equation, u equals x minus y, and add to that the second equation, v equals x plus y, then we end up with u plus v is equal to 2x, and so x is equal to 1/2 of u plus v. Likewise, we can eliminate x to get y as a function of u and v, and we can do that by taking the second equation, v equals x plus y, and subtracting the first equation, u, so we get negative u equals negative x plus y. Adding those two together, we get v minus u is equal to 2y, which means that y is equal to 1/2 of v minus u. Using these, we get our Jacobian. Remember that the Jacobian of x and y with respect to u and v is equal to a determinant that is got partial derivatives. Top row is partial of x with respect to u, partial of y with respect to u. Bottom row, partial of x with respect to v, partial of y with respect to v. And it will be easy for you to verify that those entries should be 1/2, negative 1/2, 1/2, and 1/2. Computing this determinant gives me 1/4 plus 1/4, or 1/2. And remember, it is the absolute value of that determinant that we need to put into our integral. I've gathered together the information that we need in order to do just that, and we've got the integral. V is going to go from 0 to 3. U is going to go from 0 to 2. We determined that earlier in this process. And then the integrand is going to be v e to the now x squared minus y squared is of course the product of u and v. So ve to the uv. Don't forget the Jacobian. And then du dv. Given that order, du dv, we're first going to integrate with respect to u. And for that, I want to consider basically integration by substitution. If I let t equal e to the uv, then dt will equal v e to the uv du. And so we may have thought we needed integration by parts here, but it turns out that factor of v is part of our dt in this case. Usually we call it du, but we're already using u. So I can integrate with respect to u and end up with an integral from 0 to 3 of, I'll put the 1/2 out front, e to the uv evaluated from 0 to 2 dv. This integral is now going to become pretty straightforward. 1/2 times the integral from 0 to 3 of e to the 2v. Remember, we integrated with respect to u. And then don't forget, when we put 0 in place of u here, we have -1. It gives us dv there. And now we have a straightforward process. Integrating with respect to v gives me 1/2 e to the 2v minus v. Evaluating 3 in place of v gives me 1/2 e to the 6 minus 3. Evaluating for 0 in place of v gives me -1/2. 1/2 is in front of the whole thing. And then finally, this simplifies, the arithmetic does, to 1/4 times the quantity of e to the 6th minus 7. Now, to recap this basic process here, when we need to find a transformation in order to integrate, the first thing we need to do is find expressions for u and v in terms of x and y. For example, as we just saw, u equals x minus y, v equals x plus y. Then we want to convert those into x and y in terms of u and v. And again, for example, x is equal to 1/2 times the quantity of u plus v, y is equal to 1/2 times the quantity of u minus v. That's what we just saw. Now, the first set of equations that we just wrote give us our limits of integration. The second set of equations that we just wrote give us our Jacobian. And our tip-off that we need to use the second set of equations is that the Jacobian is their partial derivatives with respect to u and v. See, those are in the bottom part of that here. And don't forget that we need the absolute value of the Jacobian. Depending on the integrand, we could use either set of equations to substitute in the integrand. In fact, I'll say use whichever set of equations is most convenient to substitute the integrand.